to this computing.
Okay, so now the recording is in progress.
Okay, that's great.
Okay, thank you. Bye. Yeah, I'm sorry for,
You are welcome.
with this new technology.
Hopefully we will reach this recording. I don't know where it is recording for the time being. So everybody is welcome to our seminar series. Today's talk is by Aurelian Goendia from Institute of Mathematics of the Romanian Academy and also Bilkent University. Our talk is going to be on probability error bounds for approximation of functions in RKHS. If I wish to say a couple of words from his biography, Aurelian Goendia studied mathematics and got his PhD at the University of Bucharest, Romania, with a thesis titled In Spectral Theory of Self-Adjoint Operators in Klein Spaces under the supervision of Ion Coloharo, I guess. And he worked mainly at the Institute of Mathematics of the Romanian Academy in Bucharest for 21 years at the Bilkent University in Ankara. His fields of interest spans between functional analysis, operator theory, and operator algebras, matrix and numerical analysis, Hermitian kernels, quantum operations, and mathematical modeling. And we all welcome him for his nice talk today in our RKHS seminars. So please, Aurelian, thank you very much. And you may start.
Thank you. Thank you so much for the invitation. And here is basically what I'm planning to talk about. As I mentioned, it's much more material that I will talk about today. Because this file will be posted on the webpage of the seminar, there will be a lot of technical details that people can see if they are interested in understanding better these things. So I will start by motivating what I'm gonna do. First, talking a little bit about concentration inequalities, and then the main motivations which are coming from uniform bounds for functions approximation and multi-view and manifold regularization of learning. Then I will just recall a few things about reproducing kernel Hilbert spaces. Probably I will skip the examples because a lot of things of that type have been most likely presented in this seminar. And then I will start going into the problems I'm interested in. So first we need a preparation for integration of functions that are vector valued, in special in reproducing kernel Hilbert spaces. And then we're going to talk about convergence of discrete sampling in these spaces and the main results. Probably I will not have time to talk about examples, but this is fine. We can have other opportunities. So anyhow, this my talk is based on a paper with one of my former student, Ata Deniz Aydın, which is published in 2021. The article it's free available, but I think that from my point of view, the archive version is much better than the published one. For some technical things. In this journal, they want 2-column pages, which is very weird for articles in mathematics, and many formulas are very difficult to read. So I recommend the archive version better than the published article. I want to say something about my co-author. Ata Deniz is now in Zurich in ETH. He's now a PhD student in mathematics. And we started this research about 6 years ago as a senior project. He was my student, and he was one of the brightest students in his generation. He had a double major in mathematics and computer science. And after talking to him, he actually told me that since I have there is a noise coming from somewhere. Okay, so talking about my co-author, he came with this idea of trying to use reproducing kernel Hilbert spaces in approximation bounds, based on the fact that I have used these techniques of reproducing kernel spaces for many years, but of course in a different for different kind of problems. And this is how our journey started. So eventually, we produced some nice results that were publishable in this journal. So let me first start with concentration inequalities, because we need this kind of setting in order to understand the problem that I will talk about. So first, I'm talking about Höfding inequality, obtained in 1963, saying the following, that assume that we have a probability space and we have n independent random variables, all of them having the same expected value mu, and such that each of these function fj is bounded, has the upper bound bj and the lower bound aj. Then for any positive epsilon, if we want to estimate the probability for those points where the arithmetic mean of these random variables is epsilon away from mu, so a good upper bound for this is this exponential. So n is the number of independent variables, epsilon is our accuracy, and this bj and aj are the bounds. So this was published by Höfding in 1963. Now, probably the most well-known concentration inequality is that which is called Chebyshev, sometimes otherwise Bianet-Chebyshev, and the general form is Markov Bianet-Chebyshev inequality. So this inequality can be stated in the following way. Again, we have a probability space. Now we have a Banach space calligraphic B, and we have a function h defined on the open interval 0 plus infinity with values in the open interval 0 plus infinity. So it is not allowed this function to vanish anywhere. And we want this to be non-decreasing. And let G be a function defined on the probability space X with vector values in the Banach space calligraphic B, be a measurable function, Borel, because we are using here the Borel sigma algebra. Then for any delta positive, if we want to estimate the probability of the set of those points on which the norm of G is larger than delta, a bound can be, an upper bound can be obtained as 1 divided by h of delta, integral over x, h of the norm of G of x, dt of x. An interesting fact about this inequality, if you look at it, is that the function h does not show up on the left side. So it is only on the right side. And this actually is a very general form of this inequality. But okay, I'm skipping the proof. Many times, this inequality is used for the function h of t, t to the power p, for some p strictly positive real number. And in particular for p equals 2, we have the following inequality. So here the upper bound is 1 divided by delta square, integral of the square of the norm of G of x with respect to p. the classical Bianame-Chebyshev inequality, which is for only one function. So we estimate the probability where the function f is k sigma away from the expected value E of f, is upper bounded by 1 divided by k squared. So k is an integer number or can be a positive number. Here are the usual notation. So sigma is variance and E is expected value. This inequality is very important in probability theory. Why? Because it actually makes the relation between, in probability terminology, between the first moment, which is the expected value, and the second moment, which is the variance of the function. It has many applications. But anyhow, now we are coming closer to what we want to do. I have to talk a little bit about the beginning of the learning theory. And one of the classic is Vapnik and his co-author Chervonenkis. So this is related to what they call statistical learning theory, which is very much based on concentration inequalities. And I'm recommending here two books of Vapnik, 98 and 2000, and the paper of Vapnik and Chervonenkis, in which they considered a very important concept in this statistical learning. So let us consider capital X a data space. This is in the Cartesian product of the Euclidean space times R, on which a probability distribution is defined, but in general, it is not known. And we have a set, calligraphic H, which is a hypothesis test. And we also have a loss function, such that one wishes to find a hypothesis H that minimizes the so-called expected risk. So we are integrating the loss function V with respect to H and X, and then with respect to the probability P. But in general, P is not known, and everything we can actually consider is the so-called empirical risk, which is the arithmetic mean of the loss function evaluated at H and Xi. Of course, this depends on the hypothesis small h. And we have a finite set, so we have actually a sample from the sample set. Vapnik and Chervonenkis theory measures the probability with which the maximum distance between the expected risk and the empirical risk falls below a given threshold. So this is an object that we would like to understand, but we cannot touch it. And this is an object that we actually can construct, and we can use in our calculations. Okay. Now there is this very strange but very important definition of dimension in the sense of Vapnik and Chervonenkis, for short VC dimension, which is defined in the following way. So we have this hypothesis set calligraphic H, we have the loss function V, and then this dimension is a maximum cardinality of finite subsets Y in X that can be shattered by H. Now, shatter, it's a verb to shatter in English, which means approximately broken in small pieces. And what is the meaning of this? It means that for any subset Y prime of Y, we can find a hypothesis H and a real number alpha such that Y and its complement are described exactly by these inequalities of the loss functions with respect to this alpha. This looks like a rather complicated definition, and it really is. The calculation of this VC dimension, usually it's not easy. Only for very simple situations it can be calculated, but it is extremely important in the problems in statistical learning. So I am now stating the theorem of Vapnik and Chervonenkis from 91, which is saying the following: assume that the loss function is upper bounded by capital B and lower bounded by capital A. For each hypothesis small h and sample x. And the VC dimension is finite. And let's consider a sampling data, x1 through xn, be selected according to the probability P. Then, for any eta, a number between 0 and 1, if we want to estimate, if we want to have the probability that the supremum of the differences between the expected and the calculated risk to be larger than something, then, and we want this to be eta, this something can be taken in this way. But this formulation is not very nice, so I'm going to call this guy from here delta. So equivalently for each delta positive, the probability of the supremum between these two estimations to exceed delta is upper bounded by this exponential. So it's 4e to the d. D is the Vapnik-Chervonenkis dimension, and we have this logarithm minus this n delta squared divided by b minus a squared. So here n appears again, and here n appears again. So this somehow tells us that if we really want this to be small, which is what we usually want, we don't want this to be too large, we need n quite large. Okay, now there is a paper, it was a paper of Girossi in 95, approximation error bounds for that use VC bounds. And in this situation, he actually, Girossi has done the following thing. He used the general theory to bound the uniform distance between the integral of j of xy lambda of y dy. So now lambda is just a probability distribution with finite elements. So this arithmetic mean, by reinterpreting the hypothesis set as the Euclidean space, the loss function as j, and the probability measure as the modulus of lambda y to the L1 norm of lambda dy. So we normalize it in order to get a probability. And then they got the following theorem. Assume that f is a function which is obtained by partially integrating the function j with respect to y for some function lambda in capital L1. Assume that the function j is bounded between capital A and capital B for every xy in the Euclidean space. And let h be the VC dimension of the function j. Then, with respect to this probability measure that we construct from lambda, for each eta in 0, 1, if we want to understand how well we can approximate the function by this arithmetic means of the function j sampled at xi, but here we have some coefficient. We need the L1 norm of lambda and the sign of lambda of the points xi. If we want this to be smaller than eta, then we need this this bound from here, which looks a little bit complicated. But the most important thing that we want to refer to, it's a paper from 2005 of Kohn and Raphael, referring to approximating functions in reproducing kernel Hilbert spaces via statistical learning theory. So we are coming closer to our setting. So Kohn and Raphael applied this methodology in order to obtain uniform approximation bounds of functions in reproducing kernel spaces. They consider two cases where the Hilbert space is dense in L2 with a stronger norm, and where it is only a closed subspace, a proper closed subspace with the same norm. So in this case, we give the kernel as an L2 function on the Cartesian product of Euclidean space, and assume that it is positive semi-definite. Then we can define the positive compact operator on L2 by integrating, by considering this kernel integral for f in L2. And then it can be proven that this operator, it's compact, which is coming actually from the usual theory of integral equations. And what is more important, that it is positive. And because it is positive, it has a square root. And the square root of this operator is exactly the operator induced by the square root of the kernel. Since k is positive definite, this can be defined. And here I'm just recalling some operator theory terminology. So recall that in a given Hilbert space calligraphic G, if we have a bounded linear operator T from G into G, T is positive, is TGG is non-negative for all G. And in this case, there exists a unique positive operator on the same space such that B square equals T. And because of that, this B is denoted by the square root of T, or T to the power 1/2. Now, for the other concept I used, compact, one of the characterization in this setting is that an operator is compact if it can be approximated uniformly by finite rank operators, which is something that we always like. Okay, now I'm coming to a statement which is actually very deep. Since I understood that in this seminar, a lot of presentations have been made about reproducing kernel Hilbert spaces, what actually people should realize when they approach reproducing kernel Hilbert spaces is that the fundamental idea, it's the idea of operator range. Here, it's a huge domain, and in operator theory, I don't want to go in this direction, but that might be a very important path if in this seminar there is an interest for understanding the deep meaning of reproducing kernel Hilbert spaces. So assume that K is an L2 positive semi-definite space on the Euclidean space. And then we defined that integral operator T sub K. Then the associated reproducing kernel Hilbert spaces to the kernel K is exactly the range of the square root of the operator Tk. And in this case, we can make precisely the definition of the inner product on the reproducing kernel space, which is given exactly by the inverse of this operator. Positive semi-definiteness. Okay, the meaning of this inverse is a little bit more complicated. It's a generalized inverse, but it can be made rigorous in operator theory. Now coming to some applications, for instance, for some kernels, for instance, for the sinc kernel, sinc is the usual notation in engineering, is sinus of x divided by x function. A wavelet of spline kernels we usually have the reproducing kernels a closed subspace of L2. So that actually means that this operator, this integral operator, has closed range. And TK is actually a projection. But in general, things are more complicated. For some other kernels, for instance, two kernels which are of very much interest in machine learning, Gauss kernel or Laplace kernels, HK is only dense with a stronger norm. Okay, now I would just want to recall briefly the Kohn and Raphael theorem, and then I'm moving to our main problem. So again, K is a positive semi-definite kernel in L2. H sub K is its associated reproducing kernel Hilbert space. And suppose there exist positive functions G and K, G in L2, K bounded away from 0, with this essential supremum dominated by tau. And let H be the VVC dimension of this hypothesis set, and F a function in the reproducing kernel Hilbert space. Then, if we consider this probability measure, which has a property that the inverse of the square root of TK FG is in L1 by a calculation involving Schwarz inequality, then for any eta positive, if we set by C of X this number from here, but here it's actually a function, we have that if we want to approximate the function f by these linear combinations, so actually here we have the arithmetic mean of these kernel functions, keep in mind that the square root of k is also a positive semi-definite kernel, but with coefficient C of xa. So basically it's just a linear combination that we want to approximate f. And we want the probability on which this approximation cannot be done accurately by eta. We need exactly this lower bound from here. So here we have 4 tau, the HK norm of f, the L2 norm of G, and this number. But there is one thing I want to draw your attention, that here the norm is in L infinity. So this L infinity is a weighted L infinity using the weight K. And this was actually the starting of our research, because having here the uniform norm, it's not what actually we want in machine learning. Why is that? Because the problem is that we want a good approximation, and usually L infinity norm is forgetting about if we have a smooth function, you can have a good approximate bound, but the derivatives may go very strange and wild, and for some important applications, this is not quite what we want to have. Okay, I'm gonna skip this part, but here is the starting of our main problems. While these bounds guarantee uniform convergence in probability, the approximating functions are not orthogonal projections of f, nor necessary elements of a reproducing kernel Hilbert space, and hence may not capture f exactly in the neighborhood of the sampling points, or nor converge monotonically, and then we have a really big trouble in approximation theory. Furthermore, the fact that the norm is not an RKHS norm means that the derivative may not be approximated in general, since we know that the differentiation operation is not bounded with respect to the uniform norm. Now, after having this as a motivation for the problems, let me present a second motivation, a very general learning problem in machine learning called regularized multi-view and manifold learning problem. Let X be a non-empty set. This formulation is very general. So if you are not comfortable with this bundle of Hilbert spaces, you can imagine that they are actually, that the W is actually the scalar, is a real line. We can work in this either by real Hilbert spaces, which is usually done in machine learning, or by complex Hilbert spaces, which is usually done in more general analysis problems referring to reproducing kernel Hilbert spaces, but it's not a big difference. There is a small difference in the sense that if you want to define positive semi-definite, if you are in the complex case, then this is enough. But if you want to use a real case, you have to be careful to also assume that the reproducing kernel is also Hermitian. Otherwise, it is not the right concept. Anyhow, let us now Y be a bundle of other Hilbert spaces. Again, you can imagine that each Y sub X is a real line. And let us now consider two sets of samples. One, X1, X2 through XL. We are calling this the labeled input points. And the other, XL plus 1 through XL plus U, are the unlabeled input points. More precisely, for the labeled input points, we have the labels Y1 through YL. They are kind of measurements at these points. And then we use this notation. So X is a vector J1 1 through L plus U. Y is YJJ 1 through L. And Z is a combination of these two. So let this Hilbert space be the direct sum of this. And since we also have a kernel, let us consider a function in the reproducing kernel induced by K, and let F be this L plus U tuple made up by the evaluation of the functions at X1 through XL plus U. Then, since we have a very general learning problem, we have a positive semi-definite operator M on this huge direct sum Hilbert space, which is actually made up by an L plus U times L plus U matrix, blocks. So capital MJK are the blocks. And let V be a collection, a bundle of maps that we call loss functions. You can also imagine that the loss function is only one, and you can actually take the simplest one, which is a least square loss function, which is used many times. Now, there's another operator, in this case C, which is called the combination operator, which is making the connection between the spaces where we have the labels and the spaces where we have our functions. And then the general regularized multi-view and manifold regularized learning problem is to find the argmin over all functions in this hypothesis set, which is the Hilbert space, the reproducing kernel Hilbert space associated to K, of this is arithmetic mean of the loss functions when comparing the labels Yj with what we want to have F estimated at Xj. The second term is a so-called Tikhonov regularization term, which is used in order to penalize functions which are very big in norm. And the second one, it's probably the most important, which is actually doing this multi-view and manifold regularization of the problem. I want to explain to you briefly what is this about. So machine learning is usually considered in three cases. One is supervised learning, the second is semi-supervised learning, and the third one is reinforcement learning. So I will not refer to the third one. My former colleague from Bilkent, Naji Saldi, is an expert in this. Maybe he can have a presentation in the seminar in the near future. But I'm going to talk about the comparison of the supervised and semi-supervised learning. So in supervised learning, we are doing the following. We are considering only the labeled input points, x1 through xl. So that means that for each point, we have to produce the labels. But producing the labels is very expensive operation. Many times, the labels should be produced manually by humans. And this is usually very expensive. Again, Vapnik was the one that initiated semi-supervised learning, where he said the following. Let us have a small set of labeled points, x1 through xl, and a very large set, xl plus 1 through xl plus u, of unlabeled points. You may wonder how we can use these unlabeled points because we don't have information about it. Well, you see, since we don't know much about the set X on which we are working, we try to understand the geometry of this set, the topology of this set, by using these unlabeled points. And this is a big idea of semi-supervised learning. So you see here, this geometry is somehow treated in this part. Okay, and after talking about this, okay, this is a learning function that we want to minimize. So this is a second motivation for our investigation. Why? Because in general, what we want a good approximation with functions in the reproducing kernel Hilbert space for what we can learn. So these labels are exactly how we can train our machine in order to work properly. But we have the following question. Can we make sure that we are able to approximate sufficiently well the function that actually we want to get as a model? And this actually is what I want to talk about. Now, just a few words about reproducing kernel Hilbert spaces. The story started back in the 1920s, but the first one who actually made out of it a mathematical theory was Aronshine in the 40s. And I want to mention here also a very important contribution of Laurent Schwartz from 1964, because Laurent Schwartz had a completely different perspective on these spaces. He was interested in Hilbert subspaces of topological vector spaces. And he added here, in parentheses, reproducing kernels in order to make the connection between them. This is a rather different paradigm from what we are using here. So it's more analytical than we are doing. And anyhow, it is very interesting. And I want to say that it was not properly exploited. Now, I want to mention two recent books on reproducing kernel Hilbert spaces that I'm recommending to everyone trying to have a good introduction to these spaces. And probably Amir Hoja will use these textbooks in the preparation of the course that he intends to teach. So one is Saito and Savano, Theory of Reproducing Kernels and Applications, and Paulsen and Raghupati, An Introduction to the Theory of Reproducing Kernel Hilbert Spaces. Both of them appeared in 2016, and they're somehow complementary. Saito and Savano is extraordinary for applications. Paulson and Raghupati is extraordinary for a more theoretical point of view and connections with other domain. So anyhow, both of them are valuable resources.
I know those two books, and we have those as references on our website, and I will benefit from those surely.
Yeah.
Thank you.
Okay, so what is the point with these reproducing kernel Hilbert spaces? The main idea is the following. We want a space, hopefully a Hilbert space, which has the nicest geometry among Banach spaces. But we want this space to consist on functions on a given set X and valued either in the real or the complex field. But there's a problem because the most natural topology on the vector space of all these functions is a pointwise convergence, which is a locally convex topology. It is complete, very nice. So we want a subspace embedded in this locally convex space, but we want it to be embedded with a stronger norm. So what does it mean, stronger norm? It means that the topology provided in this Hilbert space should imply a pointwise convergence. And this is why the story starts with evaluation map and the Riesz representation theorem and all the story. So I'm going to skip this thing and just recall. I'm pretty sure that most of the people in the audience already know this. So given H Hilbert space of functions on X, we have this K kernel. And for each P, we define these kernel functions, K sub P. And we call K a reproducing kernel for H. And then H is sent to be the reproducing kernel Hilbert space if for each P, we have these kernel functions Kp in H. And the second is exactly what we want, which is a condition via Riesz representation theorem that the topology of K to be stronger than the pointwise topology on Fx. It is actually done in this way and better probably in this well-known formulation. And this is actually why we are using this strange terminology, reproducing, which is meaning the following, that actually you can reproduce all the functions in this space exactly by the kernel and the inner product in the space. Okay, there are many nice properties about this. The association of reproducing kernel Hilbert spaces to kernels is unique and the other way around. So we are safe about this. They are very nice examples. I want only to draw attention to the following theorem. Assume that H is a separable reproducing kernel Hilbert space with reproducing kernel capital K, and assume that phi n is an orthonormal basis of H. Then the kernel can be recovered from this orthonormal basis by the summation of this series, which we can make sure that converges absolutely pointwise. It can converge even in a stronger topology, but that's sufficient what we want. And what is nice about this formula is that you see here, apparently, the basis is not related in any way to K. And actually, this can be any orthonormal basis. There is something even more interesting about this. If some people in the audience have an idea what a frame in a Hilbert space is, which is a generalization of basis, then this formula is actually true for any, okay, there are some conditions on kernel. We want Parseval kernels, Parseval frames, I'm sorry. But it is valid. Why this extension, this generalization is useful? Because in general, producing orthonormal basis is not easy, but producing frames, it's much, much easier. Okay, so there are a lot of very nice properties of reproducing kernel Hilbert spaces. There are a lot of examples. I'm going to skip all these examples. They are here. And for a very long time, I was working in analysis with reproducing kernel Hilbert spaces. For instance, this respace H2 of the polydisk DN, and there are many other. In engineering, Pali-Wiener spaces and kernels are very much important, especially in electronic engineering and transmission. And then I'm gonna skip also this example is important. Why? Because, I'm sorry, I want to go here. Because even from the beginning of the theory of reproducing kernels, so 100 years ago, people realized that reproducing kernel spaces are very much associated to green functions. And later, then they realized, after the invention of Sobolev spaces, that actually most of the Sobolev spaces of Hilbert type are reproducing kernel Hilbert spaces. And we know how important Sobolev spaces are in the theory of PDE. So this is an example of the reproducing kernel Hilbert space for a boundary value problem. Okay, now what I'm gonna need, can I ask a favor to the coordinator? How long time do I need? Because we started a little bit later.
Actually, it depends on you. Whenever you want to finish, you can finish. We are all here,
but I don't...
so no problem.
Thank you.
Basically, we have 1 hour, 1.5 hour, or
okay. Thank
so
you. You are
it
very
really
generous.
depends on you. Whenever you want to finish, you can finish.
Okay, you are very generous. Thank you. I'm trying to finish in 20 minutes.
This seminar series is about generosity.
Yes.
So thank you very much.
Thank you as well. Okay, so in order to explain the technicalities of our results, we need integration of functions that are vector valued. And people that somehow stumbled in this kind of problems probably know that if you go out of scalar functions, if you go into vector valued functions, there are different ways of defining the integration. So our setting is the following. Assume that we have a Banach space E, and we have a finite measure space X. On E, we consider the Borel sigma algebra. And we call f a function defined on X and vector valued measurable if this is an usual definition. It returns measurable sets from Borel sets. And we call it strongly measurable if it is measurable and its range is separable. If E itself is separable, Banach space, then the two concepts coincide. So, which is usually our interest. Most of the applications are not going beyond separability of vector spaces. Otherwise, we may have troubles. In order to define measurability and integrability, the approach is by using simple functions, but please pay attention to the fact that these simple functions are vector valued. The definition is the usual one. And it can be proven that a function f from X valued into the Banach space is strongly measurable if and only if it can be approximated by a sequence of simple functions pointwise. In this case, we can always choose phi n such that the norm of phi n of X is dominated by the norm of f of X for all X in X. You see, the trouble we have in these vector valued functions that Increasing, non-increasing doesn't make too much sense, because if we go in multi-dimension, we are losing exactly the order. So we have to compensate in some way. So the integral that we are going to use is a Bochner integral, which is given by this definition. A function f defined on x and with values in the Banach space is Bochner integrable if it is strongly measurable, and the scalar function x mapped into the norm of x is integrable. In this case, the Bochner integral of f is defined by using approximation with simple functions. So the integral of phi with respect to mu is exactly, for simple function, it is exactly the sum of bk mu of ek. And in general, if f is not the simple function, we are using any sequence of simple functions converging pointwise to f, and such that the norm of this sequence of functions phi of x is upper bounded by f of x for all x in x, which we can always get. We can prove that this definition is correct. It does not depend on the chosen sequence of approximating with simple functions, and then the Bochner integral is exactly the limit. This definition can be proven to be correct, and there are many nice properties that Bochner integral shares with scalar integral, but not all of them. For instance, this domination formula holds, and we can get L1, the collection of all equivalence classes of Bochner integrable functions, and we have the norm, which in this case coincides with the integral of the norm of f of x. So we have a commutation of the norm here. With the dominated convergence theorem holds for Bochner integral as well. Okay, anyhow, what we are interested in is an old theorem of Einar Hille from the 50s. His theorem is more general, but what we want here is only for continuous linear transformations. So we have two Banach spaces E and F. We have X mu a measure space. We have F a function from X E valued, which is Bochner integrable. And we consider L a bounded linear operator from E to F. Then, if we compose the function F with L, we are getting a Bochner integrable function, and the Bochner integral commutes with the operator L. This is what we need. So I'm skipping the proof of this. Actually, what we want, why we are interested in this, we're going to use it in the case of reproducing kernel Hilbert spaces, but the proposition that we have, it's a little bit more general. It can be applied also to Banach spaces of functions which make the evaluation functionals continuous. For instance, C of y for some y compact Hausdorff space has this property, even so it's not a Hilbert space. So we have this general statement. Assume that X sigma mu is a measure space. Calligraphic B is a Banach space of functions on X, with the property that all the evaluation maps on B are continuous. In particular, reproducing kernel Hilbert spaces can be used. Let lambda be a function with the properties that, a function of two arguments, with the properties that for each q in X, this function lambda sub q, depending only on the first argument, and the second is fixed, belongs to this Banach space. In addition, if for each q the map q maps into lambda q is Bochner integrable, then the scalar map q is mapped into lambda pq is integrable for each p. In this case, the pointwise integral map lies in the Banach space B, and it coincides exactly with the Bochner integral of these functions lambda sub q, which are obtained by fixing one of the to one of the variable. So again, it's a kind of commutation property that we are going to use. Okay, now we are coming closer to what we want to talk about. So convergence of discrete samplings in reproducing kernel Hilbert spaces. I have given you two strong motivation. One was Kohn-Raphael theorem for approximation, but in the uniform norm with discrete sampling. And the second is a semi-supervised problem from machine learning. So what do we have? Assume now that H is its separable Hilbert space, which is the reproducing kernel space associated to the kernel K. And given F in H, we are taking H as a hypothesis set. And we have a sampling xi, 1 through n. We are trying to find first the optimal coefficients in order to minimize the loss between F and this approximation. Of course, since we are in a Hilbert space, the minimization is actually following from the Riesz formula. This, the minimizer is exactly the orthogonal projection of F onto the span of the kernel function K sub y. We may assume without also generalities this set K sub xy are linearly independent because we can remove a finite number of them in order to keep it. And for the beginning, we recall this proposition, which is classical. It can be found in Saito and Savano textbook. Let xi be a sampling. Let the set of the kernel functions kxi be linearly independent. And consider the finite dimensional subspace, which is spanned by these kernel functions kxy. Let Pxn denote the orthogonal projection on this finite dimensional space. Then it can be actually calculated by using the inverse of the Gram matrix. The Gram matrix associated to the kernel is a capital N times capital N matrix made up by the entries K of xj, xi. Since K is positive semi-definite kernel, this Gram matrix is positive semi-definite. Since the functions kxi are linear independent, this Gram matrix is invertible. So then we can take gamma n, which is the inverse of this Gram matrix. And then we can use this the entries of the gamma n in order to calculate explicitly this orthogonal projection. Once again, if you want to understand better reproducing kernel Hilbert spaces, and this is transparent here, reproducing kernel Hilbert spaces are operator range objects. Okay, so we have this formula for it. I'm not going through the proof. And this is now what we are interested in. Consider a countable subset of the sampling set capital X. This is called a uniqueness set if the set of these kernel functions k, x sub y is a total set in H, which equivalently can be stated in the following way. For every function f in H, if f is vanishing at xa, then it implies that f equals 0. So this deserves its name as uniqueness set. And now a theorem from Saito and Savano. So this C15 is exactly Saito and Savano. HK is our reproducing kernel Hilbert space. Xi is a uniqueness set. Such that kxi is linearly independent. We have the notation for the Gram matrix and its inverse gamma. Then we can always approximate the function f as this kind of sampling, discrete samplings with kernel functions, you see, these are numbers, these coefficients are number, and the limit holds in the topology of H, which is a topology of the reproducing kernel Hilbert space. In addition, the distance of this approximation is decreasing monotonically. In particular, we also have a realization of the inner product of the reproducing kernel Hilbert space exactly by this series. Okay. Now, this corollary, if xi is a uniqueness set and yi is a sequence of f, now we want a kind of interpolation problem. Suppose that yi satisfies this inequality. So the supremum of this double sum, yi, gamma ij, and yj bar, it is very apparent to see that this is nothing else than taking this gamma matrix, the inverse of the Gram matrix, and this is exactly the inner product of gamma y, y. So if we have this assumption, then there exists a unique function f in H with the properties that it interpolates at the point xi exactly with the points yi. So again, this is what we are actually interested in, this uniqueness. I'm going to skip the proof here. And now for the last 10 minutes, I will only talk about our main results. We have a probability measure space. We have a reproducing kernel Hilbert space. And this is denoting the norm. Now comes the important part. On the measurable space, we define a new measure, P sub k, which is given by the measure with the properties that the random Nicodim of it with respect to P is exactly Kxx. What is Kxx? Are exactly all these functions on the diagonal of the kernel. So Pk is absolutely continuous with respect to P, and this function K of xx is exactly the Radon-Nicodim derivative. So we are producing actually a new measure on it. And now, here is why we need all this Bogner integral. With notation and assumptions as before, assume that lambda is a function defined on x and scalar valued, which is measurable, and such that it is in the L2 space induced by this new measure P sub k. Then the Bogner integral of these vectors, they are vectors. Why? Because kx is a function, yeah? Kx is a function, so we're not actually, we're integrating here a vector valued function with respect to B exist in the Bogner sense. In addition, if we associate to each lambda in L2 this Bogner integral and call this LPQ of lambda, this is a bounded linear operator and actually is a non-expansive. Non-expansive means that the operator norm is less or equal than 1. And this is actually one of our main objects. I'm going to skip through the technicalities of it. Now, an important part of our construction is referring to a new kernel that we have to define. So with the notation as before, this HP is a reproducing kernel Hilbert space contained in the given reproducing kernel space H. And we can calculate Kp, the reproducing kernel of this, which is obtained by this integral. Here it's a little bit of problem because I don't assume that K is strictly positive definite. So K of ZZ may vanish, but in this case, due to the Schwarz inequality, we can take the value of this 0, because clearly if K of ZZ is 0, then K of XZ is 0 for all Z. So we calculate actually the reproducing kernel of the new space. And now we have our first theorem. assume that with all the notation, if lambda is a function in L2 with respect to this measure pk, f is a function in the reproducing kernel space H, and n is a natural number, delta is a positive number. I want to consider the set of all the n tuples x1 through xn with the property that the approximation in the norm of H, this is important, this is a norm in the reproducing kernel space, of the function f by this discrete sampling with respect to the kernel functions is bad. That means this approximation is lower bounded by delta. Then considering p and the probability, the product probability on a Cartesian product x to the power n, and defining the bounded linear operator LP that we constructed by the Bochner integral, we have this inequality. So the probability of this set where the approximation is delta bad is upper bounded by the sum of these two objects. One is 1 divided by delta square, the square norm of f minus LPK lambda, and the second is 1 divided by n delta square, the difference between the square of the lambda in L2 of xpk and the square of the operator LPK of lambda. So this is in L2 of xpk, and this is the square of the norm in the reproducing kernel Hilbert space H. And I want to draw attention to this inequality because of the meaning of these two terms. You see, this one is depending on n. So n larger, it becomes smaller. But this one does not depend on n. So no matter how large the sampling set you get, there is no way to make this small unless you make delta big. You see, so if you are happy with a very large approximation, which in general is not that good, then you can make this bit small, but otherwise you cannot. And this is actually the novelty of our result, because many people said, okay, do we want to use machine learning for this the different kind of learning with kernels, and we hope that we can get a good approximation with this, but there is a very serious obstruction, and this serious obstruction is coming actually from here. Okay, now if you compare this with Cohn-Raphael theorem, you're going to see that this is a completely different type of approximation. Okay, so now I want to conclude only with two results. The first is a theorem referring to convergence in probability of projections. So we have the same setting, X, the sampling space, P, the probability, K, the kernel, H is a reproducing kernel, and we have a sequence, an infinite sequence of samples, and let this pi xn denote the orthogonal projection onto this span of samples starting only from y through n. Then for every f in the reproducing kernel space H and for every delta, where we consider now the set B and delta, the set of the n tuples x1 through xn, with the properties that the approximation of f by the projection of f onto this finite dimensional space is delta bad. Then for each delta positive, the link sup over n of the probability of these sets where the approximation is bad is upper bounded by 1 divided by delta square, the distance of the function f to this reproducing kernel space H sub p. Yeah, this is exactly the distance between the function and the space. In particular, only if F belongs to the closure in H of this subspace, we can conclude that the limit of this sequence of probabilities where the approximation is delta bad is zero. The obstruction is exactly from here. And I'm going to skip this lemma. I'm going to talk only about this proposition, because you know the trouble in machine learning is that we don't actually know the probability on which we are making the sampling. And I want to understand what kind of probabilities we can get in such a way that we have this space HP dense in H. So we can approximate every function in H, not every function in HP. And we have a sufficient condition, and the condition is exactly that. I want P to be strictly positive on any non-empty open subset of X. And this is actually a reasonable assumption. Why? Because most of the probabilities that we work with in application have these properties. Of course, they can have some discrete parts, and this is not good. So if they have a kind of continuity property, then we can have these kind of things. So this is here, for those interested, it's a proof of this proposition. And then here in the file, I have two examples, but I'm not going to talk about this. The first is a uniform distribution on a compact interval, in which we can actually calculate the left side of the main inequality. This is one of the example. And there is a second example, which is more analytic type. The Hardy space on the disk. The Hardy space on the disk is associated to this kernel, which is called the Seger kernel, 1 divided by 1 minus z zeta bar. It's one of the classical reproducing kernel Hilbert spaces, which is used in analysis of analytic functions. So I'm finishing here.
Thank you very much for this long and wonderful talk, Professor Gandia. I really benefit a lot, but I just want to ask our audience to have questions or comments about the talk. I know that they have to leave work, I guess, at this hour.
Yeah.
But I'm very much pleased to have these notes because there are lots of things there. And if I can simplify some of the topics you covered in the slides to real numbers, some real valued functions, etc., everything will be very clear for our students for a nice lecture or for a nice course, I guess, because in your slides, I have seen, especially at the very beginning, how statisticians should know some real analysis, integration theory, and the functional analysis. Sorry. And what I have observed my graduate schools in Rudin's book, The Measure Theory, I really enjoyed a lot. I've seen some couple of places eigenfunction expansions also used in quantum operator theory. Boumediene knows better than I do. I really enjoyed, and I wish to thank you once again a lot for your nice talk. And I would be very happy to have these slides. And if I can simplify some of the theorems from the very beginning in 1920s or 1940s.
So maybe
Is that a
just
yeah, sure,
thanks
sure,
Aurelian
Bonaidien.
for the talk. So I just want to not a question, but it's really a suggestion because there's a lot here in your talk. I mean, my suggestion is that maybe you can because you were talking about like different aspects where which were not very much exploited in RKHS theory. I think it would be nice to like give us openings, you know, because this is also like a research seminar where given your expertise in kernel methods, where do you see like entry points for improvement, you know, like where people who want to do research in kernel methods, where they can build things. Yeah.
Yeah, thank you. Actually, I want to talk to you sometime. Unfortunately, in the last 2 years, my life was very messy and I couldn't positively answer your invitation
Yeah.
before. Yeah, but I definitely would like to talk to you. Why? Because in the last years, and actually, um, this was one of my interest in this reproducing kernel Hilbert spaces. I am more interested in operator valued kernels. And there is a huge surge in vector valued kernels, which are going up to algorithms. For instance, if you want, I know a paper of Min and collaborators. They applied these vector valued kernels to the following problem. You have a black and white picture and you want to color it. So the problem is that colors, for instance, on the screen, they come in RGB. So a scalar kernel is not sufficient. You need a kernel having values in R3. And for each color, red, green, and blue. And they actually, what they actually did was, and it was very nice, which is another interest of mine, they used semi-supervised learning. Because if you are using only supervised learning, you have to color by yourself a lot of points in the picture in such a way that the algorithm will learn how to do it. But if you use just semi-supervised, so you are giving a small sample of colored points and a big sample of unlabeled points, then the result is fantastic. So this is one direction. Another direction, which I missed to say because I was already having too much, you probably are aware about kernel embedding. Our operator LPK is a generalization of the kernel embedding. And we can actually do much more things about in this direction. And this is another topic of one of my research interest. And of course, in the next months, because now I'm more settled down in Bucharest, my life is more comfortable than it was in the last 2 years. I hope I can go through the literature that you recommended in your slides, and especially about the connection with the dynamical systems, because for sometimes I was also working in the dynamical systems, and I have a huge interest in that. So the bottom line, it's a huge area here in which we can talk, we can probably cooperate.
Yeah, I think it will be nice because you have been like working on kernel methods for I don't know like 30, 40 years. And I think it will be nice to see what you have to say about about dynamics and also because because you also have developed these new representer theorems. I think it would be nice also. I don't know if you have time to just like survey all the different representer theorems, right? I mean that would be also like a nice thing on its own.
Yeah, actually, if there would be interest, I can have two presentations. One is to talk about these operators valued kernels. That might be one slot, and another will be exactly about this these representer theorems, which is just one. It's a very recent article of mine. Yeah.
Yeah, that would be great. Yeah.
Thank you.
Yeah, thank you very much. Thank you.
Well, thank you very much. Is there anybody else who wish to say a couple of words? If no, we can finish here. also the recording. I really thank you